All right, please make sure you've turned in your mini exam. Just leave it right up here on this desk. All right, we're going to get started right away. Also, if you have the bonus, turn that in now. Also, because I'm about to do the bonus side. I won't accept it later. All right, we're going to start off with this bonus question. I said go ahead and try and do example F and G, right? So we have this surface z equals 1 minus x squared minus y squared. Make sure you turn in your mini, and if you did the bonus, turn it in. When did you send it? 10/11 today? Oh, probably not then, no. All right, so that's what we had, right? I'm going to call this S1 up here, S2 down here. And I don't know if you can tell from your picture that you have, but this is what it is. It's a paraboloid. And underneath there, you have a disk, right? So let's start with the disk because it's the easiest one. The disk is S2. How do we define that disk? I'm going to say R of S2 of UV. So it's parametric. We're trying to get the parametric equations here. I'm going to put it here. What's the x-coordinate? V cosine U. Y-coordinate? V sine U. Z-coordinate is constant, 0. V is between 0 and 1 because it's a unit disk, and U is our theta, right? Is our angle, 0 to pi. So that gives us that S2. Now for S1, sometimes it's useful for us to take a look at it from the top. From the top, it looks pretty much like a disk, right? So we need to be able to draw the disk. The only difference is that the disk is not going to stay flat on the ground. The disk is going to move, right? It's like we're going to elongate it or stretch it upward. Do y'all kind of understand that? So the parametric equation for this S1, or S2, what is it? S1. This parametric equation should be exactly the same as the one for the disk, except that that z-coordinate can't be 0. And that z-coordinate is going to be dictated by the equation here that we have for z. And z is 1 minus x squared minus y squared. But what's x for us? V cosine u. And what's y? V sine u. So I could set it up like this. R of u, R S1 of uv is v cosine u, v sine u, and then 1 minus v squared cosine squared u minus v squared sine squared u. Hold on. Was it negative in both? Yeah. Okay. We could factor out a negative v squared and be left with 1, right? So you could do that. And now what's our restrictions? Same as before, right? Same restrictions. V 0 to 1, U 0 to 2 pi. Sorry, is that too small, my writing over there? Can you all see that back there? You're okay? Okay, let's look at the next example. The next one, I know it's hard to see on your picture there, but you have like it's not a cylinder, it's like a parabola that opens down like a sheet that's shaped like a parabola. It stops on the XZ plane, it's cut off right there. And then on the front side, it's cut off too. But it's cut off at an angle. And that angle is actually dictated by an equation plane, which is written down for you. So let me bring this up and jot down the information. This backside was z equals 1 minus x squared, and call that S1. This front side here, I'll call that S, well, I called it S3. It's y equals z, 2 minus z. And then this this side right here, we'll call that S2. This is z equals 1 minus x squared. And then I didn't put it on there, but the bottom, call it S4. What's that? It's the xy plane, right? What's the equation of the xy plane? Z0? Okay. All right. Let's try S1. For S1, we're looking at that back side. So I'm going to bring this back up again. We come in and look at this from the back, right? This is just a parabola, isn't it? It's just a parabola. The x-coordinate is going to vary between, between -1 and 1, right? The y-coordinate is going to vary, but it is determined by the x-coordinate, right? The z-coordinate is determined by the x-coordinate. The y-coordinate back and forth is always 0. So I can go ahead and set this up. S1, R S1 of UV. If you have the bonus, you have to turn in right now if you're just coming in, if you did the bonus. Okay. Tests are up here also. So what is it? My U is just U, right? I remember my x-coordinate, we're just going to call it, let's say U. We know the y-coordinate is 0. And the z-coordinate, so we have to be a little careful here. What you want to try and do is get U's and V's everywhere in your formula. So just see if this makes sense. If I call it V, right? And then in my restrictions, I say U goes between -1 and 1, but my V goes between where? 0 and 1 minus U squared. Now, here's why we would not want to use 1 minus U squared here. Because if you say V is exactly 1 minus U squared, then all it's going to do is draw the outer edge. It will not draw all this shaded stuff in between. If I say that my z-coordinate is V, and V is everything between 0 and 1 minus U squared, then it will draw everything, from whatever x value I'm at, it will draw everything from 0 up to that parabola. Everything from 0 up to that parabola. Does that make sense? It's a critical thing to see that difference. So you would not want to put 1 minus U squared there. Okay, what about S2? What's S2? Well, in that case, S2, we do want to be on the outer shell, right? We do want to be on the outer part of that sheet. We want to stay on the outer part, don't we? The thing that we want to change here on this blue one is that our Y needs to change, right? So let's start with how do we stay on the outside of the sheet? Well, I could write something like S2. See, R of S2 of U of V, RS2 of U of UV equals, now this time, let's let our U be our X component, and now our Z will be 1 minus U squared. That way we stay on the edge. Y'all see that? And our y coordinate, that's the back and forth, I'm going to call it v, because it does vary, right? It goes back and forth. How far it goes back and forth, I will control in its limits of integration. I mean, limits of integration, in its limits, in its constraints. We're not integrating yet. So what's my restriction on u? Same as before, -1 to 1. But now my v is stuck between 0 and... So if we look at it from the side, my v, and my y comes out like this, right? This is my v. It starts at 0, and what stops it? The equation of the plane. So when I come back here, what's the equation of this plane right here? Y equals 2 minus z, right? Well, isn't v y? Right? V is y. And then 2 minus z, but what's z for us? 1 minus u squared. So what I want here is my upper limit here of this region to be 2 minus z, but z is 1 minus u squared. So that's really just going to turn into what? 1 plus u squared. Questions? You sure? All right, what about S3? S3? Again, if we look at it from this side, that's S3, right? We're staring right into S3. It looks like that parabola again, right? Filled in, except that it comes out at us and goes away from us a little bit. It's not flat like it was before. So the x and the z coordinates should be exactly the same as what we had for S1. Right? On S1, that backside was that parabola. It just wasn't tilted. It wasn't the y coordinate wasn't changed. So that's what we're going to do. We're going to basically use this S1 right here again, but we're going to have to look at what that y coordinate is going to be. So let me try and put that down over here. R of S3, or RS3 of u, v, equals, okay, my u is going to be u, my z is going to be v, and I still have -1 less than or equal to u, less than or equal to 1. I have my v less than or equal to 0, less than or equal to 1 minus u squared. Right now, that draws me that solid, that shaded in parabola, right? But now I want to go back and forth. So how's it going to go back and forth? What's this? 2 minus v? So where are you getting that from? Yeah, that y is again, you want it to be on this plane, right? We don't want to go back and forth. We want to be on that plane. Well, if you're on that plane, that you have to satisfy that equation. That equation says 2 minus z. Z is v. So 2 minus v. What about the bottom, S4? Yeah, it's just a rectangle, isn't it? Or it's actually a square, right? Let me see where I can put this. It'd be UV0, right? UV0. U is between -1 and 1. Y is between 0 and 2. Okay. Or yeah, V is between. So on S4, I'm kind of running out of room, so I'm going to have to put it over here. On S4, since we're just a flat sheet, right, like this, and it's on the XY plane, my R S4 of UV, I'm just going to let my U and V be my X and Y, stick it onto the XY plane by putting 0 for my third component, trap my U between 1 and -1, trap my V between 0 and 2. And that should draw a nice little square. And that's it. Questions? See, all right. Now, the next thing, we did not finish from last class some stuff in our notes. We're not there yet. It was this one right here. Where is it? I don't know why it's not running that. It was example 3. Okay, find the surface area of the part of the paraboloid z equals y squared minus x squared, which lies between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 9. Now, without a picture, it might be difficult to understand what's going on here. But we have a surface, right? And this is the surface, the paraboloid. But that surface, right, that paraboloid, is being cut by 2 cylinders. And we're trying to find the surface area of the part in between those 2 cylinders. So here's, looking from the top, we have an inner cylinder and an outer cylinder, right, that came through and cut this sheet. And what's left here is what we're trying to find the surface area of. Make sense? What we need to do is try and come up with a vector equation, okay? Find a parametric equations for this surface, and then use the surface area formula from last class. Make sense? All right, so let's try and see if you can tell me about this surface. What does it look like from this right here, from this angle right here? 2 circles, right? Can you draw that region? That's basically a disk, isn't it? Except you're taking the center out. How can you take the center out of the disk? Change your limits on your variable, right? So I can draw this by doing something like v cosine u, v sine u. Agreed? And then what about the up and down on this? That z, right? Up and down? What's that controlled by? The surface itself, which is this equation, right? So since the circle is kind of like in the xy plane, we're going to let our x be v cosine u. Our y will be v sine u. That should draw me that little disk. I'll adjust the v and u to make it draw that. And then my z will just be y squared, which would be v sine u squared. Then take away v cosine u squared. That's me talking through it. Let me just write it down now. My r of uv will be, here we go with the circle, or the disk. Let me cut that out right now. What are these restrictions? 1 to 3 on v, because what that does is it adjusts the radius between 1 and 3 only, right? Doesn't go all the way down to 0. Then my u should go from 0 to 2 pi, right? That'll swing me all the way around. And now this part was the part that was the y squared minus x squared. So v squared sine squared u minus v squared cosine, Ooh, cosine squared u. Now, unfortunately, we cannot factor out a v squared and turn that into a 1. All right, so what we have right now is one of the most crucial parts of the problem, which is finding the parametric curve, right? The parametric surface, the equations for each component. Now we go back to last class and we say, well, how do we find surface area? It's right there. We do the double integral over the region D of the magnitude of the cross product, dA. All right? That's what we need to do. So we need to find the cross product of the partials. We need to take its magnitude. And that's going to be a real pain in the ass, as you will see. RU, what's the partial with respect to U? Negative V sine U, then V cosine U, then with respect to U, we get 2V squared sine U cosine U. So what I'm doing is I'm ignoring the V squared, derivative of sine squared U, 2 comes out, sine U times the derivative of sine U, which is cosine U. So that's this. Then again, the next piece, derivative of this, positive 2V squared. I can write sine U cosine U again, right? Doesn't matter which order those are in. That's just partial with respect to U. What's partial with respect to V? Cosine U, sine U. Two V sine squared U plus, or no, minus 2V cosine squared U. And now I have the distinct pleasure of crossing those, right? You ready to cross those? All right, so for my cross product, RU cross RV, I get, okay, so remember how we did this last class. Cover up the I's and then do your little determinant type thing here. So what happens if I do V cosine U times this thing? I have to distribute it, don't I? I couldn't clean this up, could I? This one right here? This one I can't. Can I clean that one up? No, can't clean. Well, oh, they're the same thing, aren't they? Aren't those the same? Maybe I should simplify that first. Yeah, let me simplify that first. 2V squared sine U cosine U plus another one of those, or another two of those, is 4V squared sine U cosine U. Yes, you could use a double angle identity and stuff there, but I'm not going to. I'm just going to keep it. Okay, so back to this. V cosine U times these two, which gives me 2V squared sine squared U cosine U minus 2V squared cosine cubed U. That's just this times this. Do you agree? Minus this times this. So minus, what, 4V squared sine squared U cosine U. That's just the first component of the cross product. Now I need my second component. How do we get second component? Well, we cover this up, and then we do determine again, then subtract it. So let's do, the way that I do subtraction is I'm just going to do this, and then I'm going to change its sign, and then like do it the normal way, and then just change the sign, right? That's what subtraction would be like. So what happens when I go here to here? What do we get? Negative 2v squared sine cubed u, right? But then I'm going to want to change the sign. So it'll be 2v squared sine cubed u. I don't know if y'all are looking, give me the look of it's the end of the semester, or what is that? It's this and this, right? Now this one times this one, we get a positive, but then we're going to subtract this and become a negative. So negative 2v squared cosine, sine u cosine squared u. Then I do these, right, minus this. But then it's really going to be plus, isn't it? So what's this times this? 4v squared sine u cosine squared u. So it'll be plus 4v squared sine u cosine squared u. Oops. Sorry, let me turn this off. Last one. So we look at what ignore these and do the regular determinant on this one so we don't have to change the signs. So I'm going to have to continue over here. What do we get? Negative v sine squared u minus v cosine squared u. Done. Okay, now before I go trying to find the magnitude of this nasty thing, I'm going to try and clean some things up. I see right here, right away, if I pull a negative v out, I'm going to get a 1 there from Pythagorean identity. So I know that that last component is really just what? Negative v. Can I do anything on this first one? Well, let's see. 2v squared sine squared u cosine u, and then 4v squared sine squared cosine u. Aren't those the same terms? I just have 2 of them here and minus 4 of them. Agreed? So I could really just say, that's not there, right? And change this to a negative 2. Now look at these two right here. Can you do anything here? Pull out a negative 2v squared cosine u. And what would you be left with? A cosine squared u plus the sine squared u, that would turn into a 1. Right? So what did we pull out again? Negative 2v squared cosine u, that's what we pulled out? Can we do something similar in this second one over here? Yes? These last two here are the same, aren't they? So we can put those together. So again, why don't I save myself from having to write all this down? This will just become a plus 2, and this one's gone, right? Because I had 4 of them and I had negative 2. What can I factor out of these? 2v squared sine u, and then we'll get Pythagorean identity there. Isn't Pythagorean identity great? 2v squared sine u. And boy, I've really cleaned it up quite a bit. Negative v. What's up, John? This one right here, it used to be a 4. It used to be a negative 4. This right here? This one. When I did this times this, right? And I had to do this times this. Oh, wait, no. Is this times this times this? Okay, are you asking like how did I get this? Okay, well no, because if you have a question, I need to make sure everyone gets it. On these two terms, I pull a negative 2v squared cosine u out. I'm left with a cosine squared u plus a sine squared u when I factor that out. So out of these two, I factor out this. It leaves me with this. This turns into 1. Then that becomes this. And then the same exact thing happens over here. That turns into this, and then we have the negative v from factoring out the negative v there. What is the magnitude of this? So what's the magnitude of RU cross RV? Well, that's the square root of the sum of the components squared. So 4v to the fourth cosine squared u plus 4v to the fourth sine squared u plus v squared. Yeah, factor out a 4v to the fourth from the first two, and you're left with a cosine squared u plus sine squared u, aren't you? Which turns into a 1. So you have a 4v to the fourth plus a v squared. Agreed? And I can even go further with that. I can say that's the square root. I can pull a v squared out of there and make that 4v squared plus 1. And what do you do if you have a v squared under a square root? Just pop it out as a v. Square root of 4v squared plus 1. Y'all still there? That's the magnitude of the cross product of the partials of the parametric surface. And to find the surface area, we want to integrate that over D. But we already had our restrictions on D, didn't we? Like our double integral restrictions. They were, what were our two variables? U and V, were they both between constants? Yes? It was 0 to, no. Well, 0 to 2 pi, I can do that one, right? Then I can go 1 to 3. And then I do V root 4v squared plus 1 d what, d what? U is the angle, right? So that's on the outside, dv, dv, du. And this right here, my friends, I will leave to you. All right? I'm not going to finish that out. But I will tell you what the answer is. That's a basic substitution. You make a substitution of 4v squared plus 1. The derivative of that is 8v. You're off by a constant. You work through it. And you get approximately, when it's all done, decimal approximation, 111.99. Whew, that's a lot of work, huh? So last night I was watching the Oklahoma City game. I said, man, wouldn't it be nice if I just made a thing that crossed our products for us, did the partials, did the cross product, simplified it, and then found the magnitude. So I did that. And it works pretty good. So we just had, what was it? It was V times cosine U. It's not typing. I should turn it on. It was V times cosine U. And then it was V times sine U, right? And then, so I'm putting in the parametric curve right now. It was 1 minus V squared, right? And then all I have to do is hit this little update button. Yes, it's okay. So here's our partial. Here's the cross product, simplified. And then the magnitude. Now, Mathematica has some issues with the variables because it wants to use complex variables also. So because I was getting kind of tired and the game was going into overtime, I just decided to leave it. But we can, I think, obviously see right here that we could factor out a v squared v squared, and then we got our Pythagorean identity, and it becomes the 1, so we get 4v squared plus v squared. Oh, no, sorry, this is v squared squared, so it's v to the 4th. So it works out, right? But what's even better is after that, I was like, you know what? It'd be nice if I could compute that integral too. So this is it right here. Oh yeah, well I already did it. It was there. But that's it right there. Verifying the answer. All right, that's it. We are done with 13.6. It's taken us roughly a day and a half, almost a day and a half to get through 13. Do you see why I've said this is so hard to get through the end of this book? I mean, it is. These last 3 sections just take a long time. Surface integrals. That's where we are. I'll keep that calculator around. $13.7. All right. So if you're given a scalar function f on a surface, now compare this to the previous sections where we had scalar function on a curve, and we defined the line integral, right? Scalar function on a curve was a line integral. Here we're given a scalar function on a surface, and we have the vector equation of that surface given by the parametric equations, r of uv with uv in d. Then the double integral over s, okay, it has to be double, not a single, because it's a surface, not a line or a curve that we're integrating over, of f ds, so this means with respect to surface area, not with respect to arc length, turns into the double integral over d of f of r of uv. What does f of r of uv mean? We evaluate f, replacing our x, y, and z in that function with the components of the vector function. So that's what that means. Just plug the components of the vector function into the scalar function. I'll show this in an example. Okay, so that's your function. And then times ds is your differential with respect to surface area. But what's surface area? Surface area is this, right? Didn't we just say that? Previous section, surface area is this. So all we're doing now, is we're taking our surface area and we're adding a scalar function in front of it. Okay? In that little program that I just brought up, that I wrote last night, I put in the vector, the surface, and then, I don't know if you noticed this, but this says, what's the scalar function? And I used 1. Because if that scalar function is 1, it is the surface area, isn't it? It's the same thing. It's the absolute value of the cross product. What we're doing now is we're saying, well, what if it's something else in front? You can kind of look at it this way. What was the double integral of 1 over the region D? It was the area of D. What was the triple integral of 1 over the solid E? It was the volume. What's the double integral over S of 1? It's the surface area of S. Does that make sense? That's what this is saying. If this is a 1, right? If this is a 1, then this right here is the surface area of what you're integrating over. But what if it's not 1? And that's what this section is about, or at least the beginning of this section. So here's an example. Find the double integral over S of xyz ds, where S is the part of the unit sphere above the cone, z equals square root of x squared plus y squared. Now, I included a picture. Again, this is where things can get tricky. I mean, what if you're doing a problem? You don't have the picture. You have to understand, you've got a sphere, right? The surface is part of the sphere. It's the part of the sphere that's above a cone. So you have to visualize the cone coming in and intersecting the sphere and creating that little red cap, right? And then you have to figure out, how am I going to figure out the R of UV for that cap? What's the R of UV for that cap? What do you think? Circle two different parts? Okay, so if you look at it from the top like this, you could look at it as a circle, right? That's being pulled out towards us. Do you know basically, do you know how it's going to get pulled? Like, what's telling you how much it gets pulled out by? That's the sphere itself, right? Do you have an equation for a sphere? Okay, because you're going to need that, right? You have to have that if you want this to work. You all following me? So we're trying to come up with the parametric surface. So y'all have to understand, the hardest part of these problems right now is defining of the parametric surface part. Then you do all the cross and everything else, and that's a different story. But you need this part first. Okay, so let's try this approach. This is not the approach I initially went with, but let's try it. All right. Let's see what happens here. That's the preferred way. Yes. Spherical, because how do you draw that region of the sphere? You keep your radius stuck at what? 1, and you swing it around between some angles, and you draw the whole thing, and it's done. Yeah. Do y'all like that idea? Because I like spherical is the preferred way to go about this, because the region looks spherical. I mean, yes, you could project its shadow down, and maybe we'll talk about that option also. Let's start with spherical, okay? We'll start with spherical. If we start with spherical, what are the equations for sphere? Radius, was this radius 1? Yes, unit sphere. Okay, so what is the parametric equations that draw the surface of the sphere? Sine u cosine v, sine u sine v, cosine u. Now you have to remember, u was kind of like the phi when we first did spherical coordinates. It's the one that's between 0 and pi, and the v is the one that goes all the way around, 2 pi. So remember we had theta went all the way around, and phi was measured from the top down, right? From the top down. So to draw things, my v is what spins me, and then my u is the one that brings me down. Brings me down. How do you draw it? I should stress to you, this is what draws the entire sphere, right? That's not what I want, right? This is the whole thing. This is the whole sphere. I do not want the whole sphere. The only reason I wrote that down is so that you would know which variable is which in this. Okay? So what do we want? If we're just trying to draw the cap part of the North Pole, do I want my theta to go all the way around? Yes? And I want my radius to be what? Unit sphere. 1. Well, that's already taken care of, right? There's like a 1 in front of all these. It used to be a row, but row is 1 here. And then, how far do I come down? 0 to where? To where I hit the cone, right? What's the angle that takes me to the cone? Pi over 4, you think, right? Well, let's verify that, okay? Does everyone understand, though? Right now, I'm happy with saying that, not theta, sorry, that my v will swing all the way around. It's just a question of how far to let my u go, right? How far should I let that u drop so that when it hits the cone, I stop? So one way to do this would be, take a look at this thing You have your cone coming out of it like this. It's hitting, right? If we cut this thing in half, right, just slice it right down the middle, then we would be looking at it like this. And if we slice it down the middle, let's say we had the x-axis was here, let's say the y-axis was here, and let's say when I cut it down the YZ plane. So I cut down the YZ plane so that I'm looking at this. This is Y and this is Z. Then what's the equation of that circle? Right here. What's the equation there? Z squared plus Y squared is 1. What's the equation here of this? Well, what was the equation of the cone we were given? Z equals square root of x plus y squared, right? That was the equation of a cone. But if we've cut it down and we're looking on the YZ plane, what's x? 0. So if x is 0, then this is z equals the square root of y squared, which means z equals y, which means that this is the perfect diagonal, isn't it? Which means that the angle here is 45 degrees, or pi over 4. Which means the angle that I want, which is u, right, is this angle here, should also be pi over 4. And we'll have that quick discussion now. Your calculator needs to be in radians, not in degrees, unless the angles are given in degrees. Even if you're doing inverse trig functions, always be in radians. All right. Any questions on how I recovered any of this? So I've got this vector function, right? And I have my restriction. I'm going to go ahead and put my restriction on u. What is it? Pi over 4. Okay, so that's what I just was able to figure out. Now, what is the scalar function in this problem? What's f of x, y, z in this problem? It's x, y, z. For us, what's f of r of uv? This is what I was saying. You know, what does that mean to take a scalar function and plug in a vector function? Well, that means you replace all your x's with the x component of your vector function. You replace all the y's with the y component of your vector function. You replace your z's with the z component of your vector function. What's the x component of my vector function? Sine u cosine b. Then sine u sine b times cosine u. What else do we need in order to figure out this integral? Magnitude of the cross product of the partials, right? I need that. Do you think I'm actually going to take time to do that? We actually did that before, didn't we? Last class, weren't we asked to find something about the unit sphere, and we had to do the partials and we had to do the cross product? We did, but I think I can just do it here also. Right, this is all I need. Do you all mind if I do it this way? Any objections? You realize what you would have to do though, right? Partials, cross sum, all that and less. Simplify. So what's our vector form of this? Sine u cosine, damn it, sine u, thank you, cosine v, sine u, sine v, cosine u. You know, sometimes you do, it depends. To be safe, I like to. Well, I don't like that at all. I think it came out to be sine u or something, didn't it? Look back in your notes from last class. I think we did this. Look back. It was example. It was sine u. We did that on, what problem was that? Damn it. Just so everyone can look back if they want. Example 2. We computed it. Yes, find the surface area. So we had to do that. So it came out to be sine u. Now I'm sure this somehow simplifies things. Things work out and turn into ones and. So all of that is sine u. One thing to note is that I don't need the absolute value because u is between where and where. 0 and pi over 4, and sine is always positive when you're between 0 and pi over 4. So the absolute value did not matter. Just pointing it out. All right, so here we go. If we want to do the double integral over s of f of x, well, yeah, f of xy ds, this turns into the double integral over d of f evaluated at the vector function uv, r of uv, times the magnitude of the cross product of the partials dA, which for us is all of this, right? That's our f times the magnitude, which is here, which just makes us have, what, a sine, another sine u in there? So we have double integral. How many sine u's do we have? 3. So sine cubed u. What else? Cosine u. Put them together. Times cosine v sine v, or sine v cosine v. dA. And this is over our region D. Do we have the region under control? Yes? It was 0 to 2 pi, 0 to pi over 4. So in an effort to keep this all on the same page, I'm just going to bring this up here. This should be integral, double integral, 0 to 2 pi, 0 to pi over 4, sine cubed u cosine u, sine v cosine v, d. So which one? Du dv? And then you evaluate that. You could actually split it up because here we got v's, here we've got u's. So you could split it into 2 different integrals. How would you do the sine cubed u cosine u? How would you integrate that? Basic substitution. How about sine v cosine v? Basic substitution also, right? In fact, I think we could probably do these mentally, couldn't we? Half sine squared v. So if you do those separately, this first one would be 1/4 sine to the 4th u evaluated somewhere. I'll let you think about that. Times this one will be 1/2 sine squared v evaluated somewhere. So which I split it into 2 separate integrals and multiply the answers together. Which limits go on the u one here? 0 pi over 4. And over here, 0 2 pi. What's that? What's this? 0? Right? And 0 here? that just give you 0? So what I'm going to do is come back over here. It's my little calculator. This is my circle right here. I'm going to throw it in here. My function is x times y times z. And this one should go from 0 to pi over 4. Something doesn't seem right. Oh, I have them backwards. Yes. That's right. It's not, but it is wrong. 2 pi. And you have to ignore something here, okay? This is not surface area. This is the surface integral. Surface integral. Okay, the answer is 0. But it was surface area until I decided to throw this in here and be able to change it. So the answer is 0. All right? Any questions? Is it all right if we just leave it like that and not bother trying to do it a different way? Just be happy with the spherical coordinates on that one? All right with you? All right. So here are some applications. Oh, I didn't point out the name of this, right? It's the surface integral of a scalar f over s. Just make sure, because we're starting to get a lot of these different variations of integrals, and we want to make sure we understand the naming conventions on these. Without giving you any examples, this is probably makes pretty good sense, right? We've done enough of these now. If you're given a surface, S, and you know its density at every point on the surface, then the mass is just the double integral over the surface of the density function. Then the center of mass can be found x bar, y bar, z bar with those formulas. No, because it's not over a curve. ds, remember in this, ds for us is the magnitude of RU cross RV dA. And the S becomes the D, the region of integration. Okay, special cases. I'm not real big on special cases, but the book is very big on special cases. So most of the problems in the homework, if you've tried some of your homework, most of the problems in your homework are these special cases. So it says here that if, by some chance, the surface can be written z is g of x, y. That means your x is just x. In other words, x is like u, and y is v. And then the z is some function of just u and v. If it can be written that way, then this becomes this. So you plug into the function, you plug in x, you plug in y, and you plug in z. But z is your function of your function g, so plug it in. And then this is the magnitude of the cross product. So we did that back with surface area. We showed you this. That if z was a function of the two variables x and y, your surface area formula became this. You can look back on note where's the special case? 13.6.9. It was the special cases of surface area. And if you look at that, you'll see that this was what that cross product, magnitude of cross product is. So we're just throwing that in there instead and doing this. All right. This problem's going to take a while. Oh, I forgot. I'm going to show you one thing I forgot to put in the notes. I would like to put in an addendum to the notes. So please add this as 13.7.3b. So right after 13.7.3, just put, and it's very, I'm going to not be very precise with the notation. I'm just going to put here, if S is made up of S1, S2, Sn surfaces which intersect only on the boundaries then the double integral over S of f of x, y, z ds is equal to double integral over S1 plus double integral over S2 plus double integral over S3 plus all the way out to double integral over Sn. We've seen things like this before, haven't we? We've seen this. We've seen that if you had like a region in two-dimensional space and we wanted to integrate over that region, we could split that region up into distinct, where the union of those regions made up the original, right? Well, this is saying if you have a surface that's just a bunch of surfaces put together where they don't overlap each other, they only touch on their boundaries, then what you can do is to figure out what the surface integral is of f over the surface, then you could just look at it as adding up all the surface integrals on each of those individual little surfaces. Okay? We've done it with everything else. With curves, we said if we have a curve and it's the union of finite smooth curves, and we can just do each one curve. Same thing here with surfaces. I kind of need that to do this problem, because it's saying find the surface integral of x, the function x, with respect to surface area, right? Where S is shown below, the entire surface. So this is like a cylinder that's been cut off. Has a blue side, has a green part, right? Greenish part, and then it has a backside which is red. Okay? So it has three surfaces. Those surfaces don't overlap each other. They only hit each other on the boundaries. And therefore, we can break this up into three separate surface integrals. Now, let me try and give you some heads up as to where we're headed here, okay, because this is starting to become tedious. What did we do when we had curves, a bunch of different curves that we wanted to integrate over, line integrals, but those curves enclosed a region? What happened? What did we have? We had Green's theorem. We said if we're trying to do curve integrals, but those curves come back together and it's a closed curve and it encloses a region, then Green's theorem says we can turn the line integral into a double integral. Well, guess what's coming? If we're trying to do a surface integrals, and those surface integrals enclose a solid, then what do you think we're going to be able to do? What do you think? Some version of it, right? That will convert it from the surface integral into what do you think? Triple integral, exactly. There's general versions, yes, of Green's theorem. And we have different names for different things. But that's what I'm trying to get at, is that this would be an easy triple integral. Because we just go to like a polar coordinate or cylindrical coordinates, right? We have a top cap, a bottom cap. We've done things like that in in triple integral section, chapter. So this would be a fairly easy triple integral. A surface integral, well, we're going to have to find parametric equations for each surface. We're going to have to cross and magnitudes and all that crap, right? Well, eventually we will see that we can do this. We can convert it to a triple. Here we go. We're not there yet, though, so we have to do it this way. After you suffer, just like the limit. You get the derivative after you do the limits. You get the derivative formulas. So I'm trying to do this, and I've got that picture. I'm going to have to grab myself a copy of this real quick. It's going to be huge. Yeah. I heard that. I didn't pick it up on mic, though. At least I don't think I did. Okay, here we go. All right, let's go with the easiest out of all of these. Which one is the easiest? X is 0, that backside, S1. We'll call that S1. We'll call this one S2. Call this one S3. Look at that, I'm color coding them and everything. Okay. S1. What is it? 0 because X is always 0. V cosine U, V sine U. Now, could you tell from the picture what the radius was? Oh, you can tell from this equation what the radius is, right? So the radius is 1. So V goes between 0 and 1, and U goes between 0 and 2 pi. Let me say something. I hope I spent enough time in the previous section going over this stuff, because the book really it's just right through it. I mean, there's really not, they want you to spend a lot of time looking at computer algebra systems and graphing cool parametric surfaces. They don't really, I don't think they address the amount of time that's required to really get your head around how to do these surfaces properly and get comfortable with them. So I hope that to you now is somewhat trivial now, right? I hope. That was kind of why I spent a whole almost day and a half on it. What about S2? Okay, the points on S2 have to stay with the radius 1, don't they? And they have to be on a circle. The only thing that changes is the x-coordinate, doesn't it? The x-coordinate goes back and forth. The x-coordinate goes back and forth, but as far as YZ, they all stay on that outside edge. If they stay on that outside edge, I just need a circle to be drawn. How do I draw a circle? Cosine U, sine U, right? I don't need a V in front of it because I don't need to shrink it down. I need to keep it on the outside. But those need to be which components of this? My Y and my Z. So how about cosine U, sine U like that? Now what about my X component? It is changing, right? It's V, right? It is changing. It's V. And it's in between 0 and this blue thing, and that blue thing is 1 minus Z. So my U is between 0 and 2 pi, and V is between 0 and 1 minus sine U. Because what's Z? Z is sine U. I forgot S. Oh, no, there's S3. Where did my S3 go? Did it disappear? S3, I thought I put it there. S3. Just show of hands, how many of you would want me to say, tear out a sheet of paper and do the parametric equations for S3 and we'll count it as a quiz grade? How many of you would want that right now? I'm just curious. I want to know how everyone feels about finding the parametric surface equations for S3. Just show me your hands if you would want that. Okay. All right. So that makes me realize, okay, not everyone is completely there yet with these, right? Not everyone. So that was more just like a litmus test, just trying to get a feel for where you were there. All right, tell me about this blue thing here. What does it look like if I look down the x-axis? What does it look like to me? Circle. So I need everything and everything inside, right? The only way I can do that is v cosine u, v sine u. That'll draw me my circle, but I need it to come towards me and away from me, and that's the x-coordinate. So I need my circle to be drawn on the... What happened? There it is. All right. So which coordinates are going to be the circle parts? My y and z, right? So v cosine u, v sine u. My x-coordinate needs to come out towards me. My x is what? 1 minus z. What's z? V sine u. Do you see that I couldn't put this coordinate, this as a v by itself? See, I already exhausted both variables that I have control over right here. In this problem, I'd only use the u to draw the circle with the radius 1 on it, right, to get just the outside edge. And therefore, I could use this v, I could use v here to go back and forth and just control the v down in these limits. Here, my v and my u are both being used to draw the solid disk, and then I have to somehow push it back and forth on the x-axis using, I can't use another variable, so I have to somehow connect it to these two. So I use that equation. My v is stuck between 0 and 1. U is stuck between 0 and 2 pi. Y'all with me? Yeah. Now, we haven't even really started the problem, have we? All we've done is set up the parametric curves here, or parametric surfaces, sorry. So now what I need to do is I need to take partial derivatives of each of these three surfaces. I need to do cross products of each of these three surfaces, and I need to find magnitudes of those cross products. And then I need to take those and plug those into this right here. So let's start with S1, okay? Let's just start with S1. I'm going to start a new page. Okay. The double integral on S1 of x ds is equal to the double integral over d of the function, right? What's our function here? X, evaluated on our curve. So what is the x on our curve? 0. Why am I happy about that? Zero, and then I'm supposed to do here what? Magnitude of all this crap, and it is crap to me now because it doesn't matter. The answer is 0. The answer is 0 because the integral of 0 is 0. They're not all going to be that easy, but that worked out pretty nice, right? It's a good thing I set it up first before I did, good thing I didn't do the partials first and then do all that and then come over here and say, oh crap, it was going to be 0 anyway. Okay, so that's 0. Now let's go to the next one. I'm going to stick with the color coding. I'm going to go with green now. What? No, is it? Damn it. I'm ready for summer. Y'all ready for summer? Whoa. Yeah. There you go. It's been done. I remember when I was a kid growing up, we played this game on the computer. It was a PC game. I wasn't a big gamer. Okay, I'm not claiming to be a gamer here. Back in that day, there wasn't no gamers stuff. Yeah, no. But there was you know how some games have like cheat codes on them that give you everything or whatever, and the code was "make it so." If you just typed in "make it so," like you got all the weapons, all the gold, all the everything or something. So I was just thinking right there, just make it so. I made it so right there. Just make it so. It's like the God mode code, you know? All right. This turns into the double integral over d of x. Now, I'm on S2 now, so let me go back over to S2. S2, what's my x? It's v, right? It's v. So I'm going to have v, and then all that magnitude crap. So, yes, I've got to go get it now. Okay, so help me out because I don't want to flip back and forth. What's my partial of r with respect to u on? Really, you've heard it this whole time? This is the first time I've heard it. What was the partial with respect to u? 0, negative sine u, cosine u? Partial with respect to v was 1, 0, 0, right? What happens if you cross this? Ru cross Rv. Yeah, that's pretty annoying. I'm just now hearing that. What do you get when you do your first cross there? 0. Okay, what about the middle one? Yes, it's cosine u, right? Not negative because it's the middle one. So we have 0, we have cosine u, and then the last one, sine u. Right? And now I need the magnitude of that. It's 1. Can I get an amen? Well, they have to be somewhat careful. I mean, if you just get like a random problem and try and do one of these surface integrals, you're probably going to be in trouble. I hope that improves. What's going on there? All right, so let's go back up here. Let's finish this problem off. I have 1 now up here, right? Times 1. And then dA. What were my limits of integration here? 0 to 2 pi, and then 0 to what? 1 minus sine of u. And I'm integrating what? V d d. So be careful. You have to get these right. The correct order here. dv du. Right? Because u was the one trapped between 0 and 2 pi. V was the one trapped there. So let's go ahead and do that. That's a pretty simple antiderivative, right? For v, 1/2 v squared. Plug in 1 minus sine u. Integral 0 to 2 pi. That turned into 1/2 1 minus sine u squared, and I'm evaluating or integrating that with respect to u. Is everyone comfortable with what I just did? Antiderivative v is 1/2 v squared. Plug in this, you get that. Plug in 0, you get nothing. It's not there. And now to do this, maybe expand it out. Expand it out and then power reduce or something. Well, I did the antiderivative of v, which was 1/2 v squared. I replaced v with this, 1 minus sine u. So that's 1/2 v squared. And then I said plug in 0 to v squared, 1/2 v squared. No, yes, that, because the 0. No, I'm not plugging 0 in now. Look, this right here, the antiderivative of that was 1/2 v squared, right? And I'm evaluating 0 to 1 minus sine u. When I plug this in here, I get this. When I plug 0 in here, I get 0. Yep. And then, well, I mean, I've come this far. Integral 0 to pi, 1/2 minus 1/2, no, minus, when you expand that out, you get 2 of those, so sine u, and then you get plus 1/2 sine squared u du. All I did was multiply that out and then distribute it a 1/2 through. I could pull that 1/2 out in the very beginning. It really doesn't matter. Let's do some antiderivatives here. I get 1/2 u, get minus, no, plus cosine u, plus, this turns into 1/4 minus 1/4 cosine 2u. Before I integrate it, what did I do here? Power reduce formula and distribute it 1/2 through, right? Sine squared u is 1/2 minus 1/2 cosine 2u, and then distribute the 1/2 through. And now integrate that, so you get 1/4 u minus 1/8 sine 2u. All of this evaluated from 0 to 2 pi. My goodness, what's the answer here? Plug in 2 pi, we get pi. What's cosine 2 pi? 1 plus pi over 4 minus sine of 2 pi, sine of 4 pi, 0. So that's gone. Then minus, now plug in 0. We get 0. What's cosine of 0? 1, right? What's sine of 0, 0? So that's just that. I think these 1's cancel. Where? Pi over, oh, right here. Pi over 2 right there. Yes, thank you. Correction. Make it unso. So that, what, 3 pi over 2? But that's just over S2, right? Just over S2. We're not doing surface area. We're doing a surface integral. If we were doing surface area, we would not have, this x wouldn't be here. It would just be a 1. But I sure as hell wouldn't try and find the surface area of this cylinder doing this. You know what I'm saying? It'd probably be a better way. But we're not doing a surface area. So let's do S. What? We're finding the surface integral, not the surface area. The surface integral. It's called the surface integral. It could mean different things. If x right here in that problem, if x was the density function, then we just found the mass. We're finding the mass. If it's the electric potential function, right, you get total electric charge, something like that. It'll just depend on what it is applied to. Electric density function. Yeah, I mean, we'll have other ways of doing this. But remember what we did? God, I can't believe we only have 15 minutes left. See what I'm saying? Every semester I think I'm going to make it, and there's just no way. These last 3 sections are so heavy. Oh, are you suggesting we go on? Oh, okay. Yeah, well, I can do that. I have no problem with moving on with this. But what I want you to see is kind of a bigger picture here, though. We started with line integrals of scalar functions, right? We had scalar function over a curve. Then after we did scalar function over a curve, we went to vector function over a curve. Right now we're doing scalar function over a surface. Next is vector function over a surface. And that's where we get flux from, for those physics people. You're basically trying to figure out how much stuff's flowing in and out of a surface, closed surface. So S3, are we okay moving on with then? Would it be hard? Well, you'd have to cross 1 minus V sine U. 1 minus V sine U. Damn it. V cosine U. Someone just verify that I am putting in the right. This is S3, right? 1 minus V sine U, V cosine U, V sine U. Yes? And then U went from 0 to... Oh, it's just, okay. Oh, wait a minute, hold. 1 minus V. Hold on a second. Go back here. It's 1 minus V sine U. Because Z was V sine U. Ooh, I thought I forgot it earlier. Okay, so that is V times sine U. And then what's our function? X, and we're going 0 to pi, and then 0 to 1. And let it go. Square root of 2 pi. Square root of 2 pi. Yeah. Don't worry about it. It's, again, Mathematica tries harder than I need it to, and that can be a problem sometimes. Add that to the other one. The other one was V cosine U sine U? Yeah, okay, we did that one. So add them up. Back to the notes. I don't know what much more I can do in 10 minutes, but I can at least talk. Oriented surfaces. So now what we're working up to now is flux, all right? If you have a surface and you compute the tangent vector, right? When you have a surface, we can get 2 tangent vectors, can't we? Partial with respect to U, partial with respect to V gives us 2 tangents. If we cross those, we can get a normal vector, can't we? If the normal vector points out away from the surface like this, if it's a closed surface, points out, that's positive direction. The other way is negative, right? It's just whatever that normal is multiplied by -1, you get the same vector pointing in the opposite direction. So that's negative orientation, that's positive orientation, okay? It talks about, you can only talk about oriented surfaces if you have a 2-sided surface. The book goes into explaining that it is possible to have 1-sided surfaces. Mobius strip, if any of you have ever heard of Mobius strip. Mobius strip? Yeah? How many of you have not heard of a Mobius strip? Sorry, I'm not going to hold it against you. Mobius strip, Mobius band? Oh, wow, then we have to talk about it. I'm sorry. So most surfaces we consider to have 2 sides, right? 1, 2. Now, of course, you could look at this as almost like a solid, because it does have some depth. But let's just say it's like a point, right? A point has no width to it. A point is a point. A line doesn't have thickness to it, theoretically. This sheet of paper does not have thickness to it. It has two sides. Okay? So an example of a one-sided surface is you take a strip, two sides, and you just twist it one time and you paste these two together like that. And you get this. Now, this is an example of a one-sided surface. If you put your thumb and your index or any, your fingers on like that, it looks like they're on two different sides, but if you follow it around and you come back, you'll get to your other finger, and then you come back around, you get to your thumb. So your thumb and your other finger are on the same side of this sheet. This is a Mobius strip. It's an example of a single-sided surface. Okay? There's also something called a Klein bottle. Have you all ever heard of a Klein bottle before? A Klein... Yeah, I had Klein bottle. Is it not there anymore? Yeah, I have a Klein bottle as my picture in Canvas. A Klein bottle is an example. Okay, that's a two-sided surface, right? So a Klein bottle is it's a container that has no volume to it. So it's a three-dimensional container that has no volume. And take a class called, for any of you math people, you will study this stuff later on in courses called topology. I've told my students in the past that I spent almost a year trying to mathematically determine the difference between these two objects. Well, a coffee cup and a donut. I mean, we can sit here and talk about what the differences between a coffee cup and a donut are very easily, right? We can sit here like, you don't eat your coffee cup, right? Donuts taste good, right? I mean, we can talk physical, we can describe differences and similarities between these two physically, visually, right? But mathematically, how are they different or the same? And that's where this whole subject topology comes into play. And I'll make it short, all right? Basically, these are both can be looked at as surfaces. And if I grab any 2 points on the coffee cup and draw any curve on the coffee cup, right? If I draw that curve, then there's a way that I can, even if I draw it like this, I can close this down. My God, guys. I can close that down to a single point, right, and never leave the surface of the coffee cup. And if I do it this way, and I go around the handle and come back down like that, I can't close it down, right? And the same applies for the donut. If I have a point here, and let's say I draw a curve and it comes back around, it goes the other side of the donut, comes back, right? I cannot close that without breaking through the surface. And so it turns out that, mathematically speaking, there's no difference between a coffee cup and a donut in a mathematical sense. They're identical. They're identical structures mathematically. So a Klein bottle is an example of a surface, I mean a Klein, K-L, yeah, I-E-N or E-I-N, I'm not sure which one it is. I think it might, E-I-N, yeah. Yeah, that's a little different. Klein bottle, the problem is that you cannot make a Klein bottle in three-dimensional space. You have to have 4 dimensions to make it. So you can only try and represent it. And so the pictures of it that you see are just representations. It's impossible to like say, hey, here's a Klein bottle. But I have one of my friends that I graduated graduate school with me got me a Klein bottle beer mug. And so it's weird. It's like the inside turns into the outside. So the inside of the glass container goes into the handle, but then the handle, so you're inside, and the handle turns and then becomes the outside of the mug too. So the inside of the mug is the outside of the mug, which means that it can't have volume to it. And so it has, you know, like graduated cylinders and beakers have like milliliters and stuff like that. It's a beer mug that has markings and just says 000 the whole way because it's a volumeless container. Yeah, and my friend used to own a bar, and he said if I brought that in, he'd always fill it up for free because I wasn't using any beer technically, right? So anyway, yeah, that's it. But see, in reality, you can't break through yourself. Just like on the Mobius strip, the Mobius strip never touches, never breaks itself. The Klein bottle is something like this, where there's a twisting in it, and when you put it together, you've taken away one of the dimensions. So it's a container that's missing a dimension, so it can't have volume to it, right? Like think about it this way: does this have area? Does that have area? Okay, twist it and put it together. Does it have area? Well, it's length times width, right? But they're the width and the length never ends. Look, if I say what's the length, you go around, you follow this edge, it'll just keep going. It never stops. It's a weird concept, but this is where I think infinity might come from. But all right, I've successfully exhausted almost the rest of class. I want to see if there's anything else that I can talk about. I can show you this at least. I can show you what flux is, okay? Here's what flux is visually. We have, let's just say, a surface. Here it's a sphere, all right? I'm going to come around here with some vectors. Now, I think I'm going to put it right there so you can see it. The green vector is, oh, I didn't mention this. There's a vector field here, okay? Now, I can't show it because, remember, it's all those arrows all over the place. But there's a three-dimensional vector field. So at every point in this three-dimensional space, there's some force, whether it be magnetic, you know, gravitational, flow of liquid, whatever it is, there's some force trying to move things in the direction of this green arrow, okay? See the green arrow? Then we have the normal vector. Now, what's the normal vector? That means on the surface, it's the one that points out. That was the cross product of those two tangents. Cross them, came out with the normal. That's the, hold on. Yeah, that's the black one. Sorry, the black one is the black one is the normal. Okay, the black one's the normal. If you take this vector, right, this green one, and project it down onto the normal, you get the red vector. The red vector is the projection. Do you see it? It's kind of hard. I got to twist this thing around to make it look perpendicular. But so what flux is doing is it's taking this vector, this red vector here, and it's kind of adding them up. It's trying to figure out that red vector is saying, look, something's trying to come out of this surface. The green arrow is trying to take it this way. The normal vector wants it to go this, like this. And so when you project this one onto this one, that's really like the net result of what's happening. And so we take that and we look at more of them, right? Here's the vectors that go with those. Here's the projections on each. So I've already done that. Now take them all out. Let me take this one out so you don't even see it anymore. And then imagine letting the number of them go to infinity, right? So what you get is out of that infinitesimally small patch on the surface, the red vectors coming out is your flow out, which is your flux. But to get it, what you're going to have to do is you're going to have to take the vector field and dot it with n, which is really like taking the vector field and dotting it with the cross product of those two partials. And that's where we're headed. That's what will give us flux. All right, so that's where we'll pick up. 13.9 is not looking very good for us. I don't know if we'll make it the way I wanted to. Thus is life.